Good morning, students. In this video, I am going to explain about next part of the unit, that is superconductivity. This is second part in the fourth unit. So this is what we are going to study in this unit is mainly definitions, terminology, main definitions of superconductivity, BCS theory, and also types of superconductors and applications of superconductors. These are all the important topics in this superconductivity. Very easy and interesting topic also. So we will see the first definition of superconductivity. Superconductivity is a from the name itself we can understand the conductivity is very high. For some of the materials, it exhibits the property of high conductivity at a particular low temperatures. That high conductivity having at that high conductivity it shows zero electrical resistance. That is explains here from this graph. You can observe from this graph the resistivity is becomes very less. You can see this graph here at a particular TC means critical temperature or transition temperature. Below this temperature, the materials exhibits very zero resistance. That property is said to be the superconductivity. This is the graph for the normal metal. The conductivity, resistivity, and the relation between the resistivity and temperature. As the temperature increases, the resistivity changes like this. Here, as the temperature change means at low temperatures, the conductivity becomes very high and resistivity becomes zero. Resistivity becomes zero means the conductivity becomes maximum or infinitive. In that state is said to be the superconducting state. This is exhibited by some of the materials like example tin, lead, and the niobium and aluminum at the temperature of 3.72 kelvins. This is the critical temperature for this tin material. For the lead material, 7.2 kelvins is the critical temperature. Below that temperature, that material is having the zero resistivity and infinite conductivity. So here niobium is having, this is the critical temperature 9.2 kelvins, aluminum is the 1.1 kelvins, etc. Some of the materials itself, by nature itself, they exhibits the property of the superconductivity at below that particular temperature. They will behave like a high conducting materials with zero resistivity. Above that temperature, above the critical temperature, they will behave like a normal materials. The examples are tin, lead, niobium, and aluminum. Here we can understand the definition from here. Superconductivity is a complete disappearance of the electrical resistance. Superconductivity we can remember like this: zero resistance at particular low temperatures. So in some materials they are cooled below a particular temperature. This temperature is known as the transition temperature or critical temperature. The zero resistivity means almost infinite conductivity. A superconductor is a material that exhibits the superconductivity above critical temperature. A superconducting materials behaves as a normal conductor. Thus, the observed phenomena is called as the superconductivity. So, from this graph, we can easily understand that zero resistivity and maximum conductivity at low temperatures for some of the materials is said to be the superconducting state. That particular temperature where they can behave like a superconducting materials, that particular temperature, that limit of temperature is said to be the critical temperature or transition temperature. Here we cannot say that all metals or all conductors are the superconductors. Only few materials exhibits this property because of the presence of the electron pairs. This superconductivity, the main reason behind this property is presence of the electron pairs. By the nature itself, by the formation of the covalent band, depends upon the structure of the periodic lattice. The electron pairs will develop in the materials. The formation of electron pairs and the flow of the electrons in the pairs. Here, in this type of superconducting materials, the electrons will flow in pairs. Those are said to be the Cooper pairs. When the Cooper pairs will develop in the materials, the superconductivity is possible in that materials. So we can understand that the basic reason behind this superconductivity is the formation of pairs or group of electrons in the materials and flow of electrons in pairs in groups. So that is said to be the superconductivity reason. So here we can understand the BCS theory. The three scientists combinedly developed this theory: John Bardeen, Leon Cooper, and the John Schrieffer. So this is said to be the superconductivity theory. This is only for reference. We can understand the main points in this reference. electron lattice electron interaction. The first point is the electron lattice and electron interaction. When the electron is moving inside the ionic lattice, as we already discussed in the previous lessons, when the electron is detached from the atom in the materials, when the electron is free electron is detached from the atom, it will behave like a positive ion. Every metal is having the periodic arrangement of positive ions, that is said to be the lattice. So if you consider the electron to lattice electron interaction, so if there is attraction between the electron and lattice, and the lattice and electron, and there is a repulsion between the electron and electron. So if the BCS theory is based on the electron, lattice and electron, this theory mainly explains electron, ion and another electron interaction, because due to that electron electron pair will form. So there is the interaction between the electron, ion and the again electron. That interaction or the attraction between those positive and negative charges will develop the Cooper pairs. So we can understand the second point, lattice distortion. If there is the attraction between the ion and electron, then what will happen due to this attractive force? Ions slightly moves from its place due to the attractive force. Then the periodic arrangement of structure will slowly distorts. Here we can understand when an electron approaches an ion in the lattice, there is a Coulomb attraction between the electron and lattice ion. This produces the distortion in the lattice structure. It increases the density of positive ion surrounding to electron 1. Due to the lattice vibration, the energy is emitted in the form of quanta or phonon. Phonon will be emitted, means due to the distance between the electron and positive ion, there is a due to the distance between the electron and positive ion, there is a interaction or there is a attractive force. Due to that attractive force, then what will happen? The distortion will be possible. The ion will slightly move from its place. Then uh, the structure will changes. That structure of the lattice is said to be the lattice distortion. So due to the change in the structure, the energy is stored, that energy is emitted in the form of quanta or phonons, is a small type of particles. And the third point of the BCS theory is formation of Cooper pairs. When the positive ion is combined by electron, then two electrons neighboring it, then what will happen? They will be a bond will form between the electron ion and the electron. Then what will happen if that bond is developed due to the some energy? That energy is said to be the phonon energy. When that bond will break between the electron ion and the electron, the phonon energy will be released, or we can say that two electrons will form a group neighboring the positive ion. Then electron 1 and electron 2 will come together between the positive ion, and then what will happen? Electron 1 and electron 2 form a group. That group is said to be the Cooper pairs. Here we can understand this, from this diagram we can understand here what will happen. This is a positive ion. Due to the attractive force of positive ion, these electrons are coming to near to the ion, and these positive ions are here. Second electron changes the positive charge. Here this is a positive ion. Here two electrons are near to the positive ion. Due to that, these positive ion will distort from its original place, and the structure of lattice will change. So here this is electron and electron pair. Here this electron and electron pair will form a group with this positive ion. This electron and electron pair which is combined with the positive ion and which is forming a group with the positive ion is said to be the Cooper pair. Cooper pair is nothing but a two electron group which formed due to the attraction of the positive ion. Here in the flow of the electric current also, these two electrons combines the flow from one place to another place. Here fourth point, zero resistance below critical temperature. This is already we know a definition of superconductivity. At a particular below temperature, that material behaves like a superconducting, having zero resistance and infinite conductivity. Maximum number of electrons will flow in that material in the form of pair of electrons. Those are said to be the Cooper pairs. Above that critical temperature, there is no Cooper pairs. And then what will happen? that behaves like a normal conductor, and that Cooper pairs will break and the phonons will release. And superconducting current. A large number of Cooper pairs drift cooperatively through the superconductor in an ordered state, forming a highly collective condensate. So, what we need to understand, in superconductor materials, the electrons and neighboring electrons form a group. Two electrons form a single group. This pair of electrons is said to be the Cooper pairs. In the superconducting materials, the electrons drift in the form of pairs, Cooper pairs, due to that huge number of electron flow is possible in that material, so conductivity will be maximum and zero resistivity will be possible at below critical temperature. Here we need to understand the properties of superconductors. As we already know the definition, zero resistance, zero electrical resistance, that is the first property of the superconductors. This graph is important. Every time when we are writing the definition of the superconductors, we need to draw this graph. Resistance and temperature. Below the critical temperature, resistance is 0, and above the temperature, the resistance slowly increases. Above this critical transition temperature, this resistance will be slowly increases and the conductivity decreases. Below this transition temperature only, resistance becomes 0. Here we can understand here from the first property, zero electrical resistance, the variation of resistance of superconductor with temperature can be measured by four probe method. This is a small experiment to measure the resistivity changes with temperature of the superconductor. This is said to be the four probe method. Here four probes are connected like this, and a voltmeter is connected and ammeter is connected here. Here the current is passed in a superconductor through current probes 1 and 4, and the current connections are given here. Battery is connected to the first probe and the fourth probe. Voltage is measured with the voltage probes 2 and 3. The resistance of superconductor can be calculated by Ohm's law. So how the resistance changes are there? We can measure using the Ohm's law and normal state. When the temperature is greater than critical temperature, then what will happen? Some resistance is developed. In superconducting state, the resistance of superconductor vanishes or becomes 0 at T is greater than Tc, superconducting state. So the and hence the voltage across the voltage probes disappears, that is V is equal to 0 while current continues to flow. So here when the resistance becomes 0, infinite conductivity will be possible. And next, persistent current. This is also a good property of the superconducting materials. Here what is this persistence? Persistent is nothing but continuation of currents. We can say that existence of current. So once the current flow is started in the superconducting state, that current flow is maintained for so much long time or for so many years, till that material is maintained that critical temperature. So if the critical temperature is maintained, the current flow does not stop. Once already initiated, that current flow will be continued. In the superconducting material, it is observed here. Once a current is started in a closed loop of superconducting material, it will continue to keep flowing. So here what will happen? The current flow is initiated using external magnetic field. The current when the current carrying conductor is started its current flow below critical temperature. So when the temperature is maintained, so then what will happen? Such a steady current, it's keep on flowing of its own around the loop as long as the loop is held below critical temperature. Such a steady current which flows without diminishing in strength is called the persistent current. If you maintain the temperature, no need to maintain the current flow here. The persistent current does not require the external power to maintain. Here in superconducting material, it's a good property. If the current flow is initiated below the critical temperature, it is maintained automatically without any external source. Only we need to do that the temperature should be maintained. That high current flow under low temperatures for a long time is having a zero resistance and no current losses, eddy current losses is not observed, no heat losses is also observed. So it will maintain a long time of more than 10 power 5 years. If you can maintain the temperature constantly, it can the current flow will be maintained for a long time of 10 power 5 years. So persistent current is one of the most important properties. Superconductor coils with persistent current flowing through them produce the high magnetic fields and can therefore act as a magnet. The current conductor which is carrying the current can produce the magnetic fields and can be act as a magnet also. Next one is the critical magnetic field. Next definition is critical magnetic field. In this critical magnetic field, the critical magnetic field refers to the maximum magnetic field strength below which a material remains the superconducting state. So two parameters which will affect this superconducting state, that is the temperature and one is the magnetic field. If you apply the external magnetic field for a particular level limit of the magnetic field, that superconducting state losses and it will becomes as a normal conductivity, normal conducting material. Here we can observe that after the H naught limit, the material behaves like a normal conductor. It depends on temperature, is characterized by both temperature and magnetic field. The highest temperature and which is the supercritical temperature, at that temperature even the weakest, here, in either temperature or magnetic field can change the phase transition between normal and the superconducting states. At a particular magnetic field where this external magnetic field will destroy the superconducting state, so the strength of critical field is zero. As the temperature decreases, critical field increases generally to maximize at absolute zero. The critical magnetic field is nothing but where the material loses its superconducting state by applying that magnetic field. That is represented with Hc of T. It is depends on Hc of 0, 1 minus T upon Tc whole square. Here Hc of 0 is the critical magnetic field at 0 kelvins. Tc is the critical temperature. So magnetic field also will affect the superconductivity. So it is depends on different type of materials. Here the some values of the critical magnetic field values are given here. For niobium 198 millitesla and lead 8.3, 80.3 millitesla, and here etc. These are all materials having the different electric and the magnetic field, critical fields. Critical current and the critical current density. An electric current flowing through the superconducting material produces a magnetic field surrounding it. As current increases, the associated magnetic field also increases. Thus, it is important to have the current flowing below a certain value is associated with the critical magnetic field. So, we already know that magnetic field changes, its temperature changes, then superconducting state also disappears. So in the same way, if a current flow also changes, because every current carrying conductor will develop a magnetic field around it. If the current flow changes, strength of the current changes, then what will happen? The magnetic field strength also changes. Then the superconducting property may disappear. So it's need to maintain the current flow also steadily. So that current flow, the particular limit of the current where that superconductivity disappears is known as the critical current value. So that is a critical current density or critical current. Here and current critical current, electric current flowing through the superconducting material produces a magnetic field. As current increases, the associated magnetic field also increases. It is important to have the current flowing through the superconductor below a certain critical value which is associated with the critical magnetic field. So, to maintain the magnetic field below the critical level, we need to maintain the current values also. The critical current, the formula for the critical current is Ic is equal to 2 pi r into Hc, depends on the external magnetic field applied or critical magnetic field. Current density is defined as the current per unit area, that is Jc. So the maximum current density at which the superconductivity is said to be the critical current density. Critical current density is nothing but it's a limit where the superconducting material lost its superconductivity. These are all about the definitions of the superconductivity. Simple main definitions are the definition of superconductivity. And next, this critical temperature, critical magnetic field, critical current, and the critical current density, and persistent current. These four definitions you please practice. We'll go for the next some properties of the superconductors and the applications of, and types of superconductors also. Thank you.